All right, let's go ahead and get started. I want to welcome you back to Unit 13. We're talking about gases, and we're specifically talking about the ideal gas law. The ideal gas law, remember, is going to be used when nothing's changing, right? We would use the combined gas law if pressure or volume or temperature were changing. But if we simply are taking a snapshot of a gas and just saying, listen, I want to know some parameter of this gas, whether it be pressure or volume or temperature or even the number of moles of gas, this is the one I'm going to use. P is for pressure, V for volume, N is the number of moles of gas, R is the gas constant, and T stands for the temperature. So there you go. That's the universal gas, or excuse me, the ideal gas law. And speaking of universal, we're going to have to determine what the universal gas constant is going to be. This R value right here is either going to be 0.0821 or 8.325, depending on whether the volume is given in liters or cubic decimeters and the pressure in atmospheres or kilopascals. So of course, if it's liter atmospheres, then you're going to use this R. If it's decimeter kilopascals, you're going to use this R. Okay, so that's pretty straightforward. So now what we're going to do is we're going to take a look at a couple of different problems to just make sure that we have a good grasp of this ideal gas law. Let's take a look. So here's what it says. It says calculate the approximate volume. So we're looking for the volume. We're looking for V of a 0.6 mole, 0.600 mole sample of gas at 15 degrees Celsius and a pressure of 1.10 atmospheres. So how would we approach this? Well, the first thing we're going to notice is that nothing's changing. Okay, it's not a situation where pressure's changing or volume's changing or temperature's changing. So we're going to use the ideal gas law. Okay, so here it is. The ideal gas law says that pressure times volume is equal to the number of moles of gas times some value of R times the temperature. Let's write down everything we know. We know that the pressure from this problem, we know that the pressure is 1.10 atmospheres. We're looking for the volume. We know that the number of moles is 0.600 moles of gas, and we're going to use an R value of 0.0821. Why? Well, because of the fact that the the pressure was given to us in atmosphere. Now, they're not asking us what unit we should use for the volume, but we may as well use the liter since that would correspond to this unit, liter atmospheres per mole per degree Kelvin. So we're going to use 0.0821 for the R. And then for the temperature, remember, it's never okay to use Celsius degrees, but it's easy to get to Kelvin. Just add 273 and you get to Kelvin degrees. So now what we're going to do is we're going to rearrange this equation to get V alone. So the original equation was pressure times volume is equal to the number of moles of gas times R times T, and we get this equation. V, I'm dividing both sides by P now. V is equal to nRT divided by P. So now let's plug things in. The number of moles of gas was 0.600. We've decided to use the R value of 0.0821 since we have atmospheres for pressure and we're going to report our answer in liters. Temperature was 288 and that's Kelvin. And then we're going to divide by the 1.10 atmospheres of pressure and that's it. So what I want you to do is I want you to actually do this on your calculator with me. So we're going to say 0.600 times 0.0821 times 288. We'll hit the equal button and divide by 1.10. Folks, on my calculator, I get 12.89716. I'm going to just round it to 12.9 liters. Okay, so the volume then is 12.9 liters. So if you have a gas, and that gas is at a pressure of 1.1 atmospheres, you've got 0.600 moles of it, and the temperature is 288, we now know what the volume is going to be. It's going to be 12.9 liters, okay? All right, now, just one more gas law problem to make sure we really understand it, and that is this. We're going to look at something called Dalton's law of partial pressures. It's really easy. I mean, incredibly easy. So here's what Dalton's law says about partial pressures. First of all, let me explain partial pressures. What we mean by partial pressures is we often have a mixture of gases, right? And what Dalton said was that in a mixture of gases, the total pressure is going to be the sum of the pressures of the individual gases. In other words, if you had, for example, 3 gases in a tank, nitrogen, oxygen, and fluorine, I'm just making this up now, the total pressure is going to be the pressure exerted by the nitrogen plus the pressure exerted by the oxygen plus the pressure exerted by the fluorine. So if you want to know the total pressure, just add them up, and that's called Dalton's law. So now let's take a look at a problem involving Dalton's law. Here we go. A gas tank contains helium at 925 torr, okay? Nitrogen at 1400 torr, and some oxygen. Doesn't say what the pressure of oxygen is. But it does tell us that the total pressure is 2800 torr. And they want to know what is the pressure exerted by the oxygen, right? So let me write the kind of the symbolism for this. So we're going to say the pressure exerted by the oxygen is equal to, I don't know, that's what I'm trying to find out, okay? That's how you write the symbol though. All right, so here we go. So the solution would be this. The pressure which is accounted for is 925 torr for the helium and 1400 torr for the nitrogen. So we know those. We also know that the total pressure is 2800 torr. So the only remaining gas is oxygen. So the pressure of the oxygen must be 2800 torr minus the sum of the 925 plus the 1400 that we have accounted for already, and we're left with 475 torr. So we can say then that the pressure, partial pressure I should say, exerted by the oxygen is equal to 475 torr. Okay, and we could change that to atmospheres if we wanted to, but no need to do that. The problem doesn't ask for that specifically, so we'll just leave it alone. All right, good. Let's move on. Okay, the following are for pre-AP students. So regular chemistry students, you can take a break at this point if you want to. You're more than welcome to come along for this ride if you'd like, but this is going to be a little bit more advanced and geared more towards pre-AP. All right, so here we go. If you have, this is problem number 1, if you have 1.34 liters of a gas at STP. Let's stop right there and talk about STP. What does that mean? Well, standard temperature and pressure, that's what it stands for. Standard temperature and pressure is this. STP is 0 degrees Celsius. So the temperature at STP is 0 degrees Celsius. And the pressure is 1 atmosphere, just like that. So that's STP. Now you might say, well, wait a minute, are you sure about that temperature? That's the temperature at which water freezes. Yes, I'm sure. Absolutely. 0 degrees Celsius is standard temperature. 1 atmosphere pressure, standard pressure. So STP means you've got 0 degrees Celsius and 1 atmosphere. Those are the conditions. So that clears that up. What would its new temperature be? Okay, when you see that word new, that tells you you're not going to use the ideal gas law. What are you going to use? You're going to use the combined gas law this time, okay? What would the new temperature be if the volume was decreased to 873 milliliters and the pressure was increased to 2.33 atmospheres, okay? Fair enough. We're going to use the combined gas law. We know that, but let's write down what we know. We know that the initial volume was the 1.34 liters, right? We know it became 873 milliliters, right? Or we can write that as 0.873 liters by simply moving the decimal place over once, twice, 3 times to the left, right? By the way, if V1 is in liters, V2 has to be in liters too. That's very important. You can't have liters and milliliters, okay? Okay, T1, they tell me that the initial temperature is 0 degrees Celsius. Well, not really. They didn't tell me it was 0 degrees Celsius, but they did tell me I was at STP, and that means 0 degrees Celsius. But Celsius is no good. We've got to put it in Kelvin degrees, so we're going to say 0 plus 273, 273. So 273 is the temperature that we started with. We're looking for a final temperature after we change other things, okay? And our initial pressure was 1 atmosphere. Again, that's standard pressure. Okay, so you have to know what STP means now. So standard pressure. So 1 atmosphere to start with 2.33 atmospheres in the end. So now we've got it all written out for us. Let's just write the formula. This is the combined gas law. This is P1V1 over T1 is equal to P2V2 over T2. If that doesn't sound familiar, you need to stop this video right now and go back and review those notes, okay? But that is the combined gas law. Manipulating algebraically, remember we're looking for T2. We're going to pull the T2 up like that, and then P2V2 was already there. We're going to pull the T1 up just like that, and that'll give it to us. Now we've got T2 by itself, and it's just a matter of plugging things into the formula at this point. So here we go. We've got 2.33 times 0.873, follow me on this, times 273 divided by 1 atmosphere divided by 1.341. Let's do this on our calculators together. Here we go. Let me turn mine on. 2.33 times 0.873 times 273, I won't bother with a 1, divided by 1.341, and I get 414.0988, blah, blah, blah. I'm going to round it off to 414. Don't forget, it's degrees Kelvin, okay? It's degrees Kelvin. All right, let's take a look at another problem. Here's what it says. It says a 32.8 gram sample of a gas has a volume of 34.9 liters, a pressure of 12.5 torr, and a temperature of 303 Kelvin. What is the gas's molar mass or molecular weight? Well, this is going to take a little bit of doing because remember, molecular weight is not in the ideal gas law formula. And also remember this, that nothing's changing, so we're going to be using the ideal gas law. So here's how we would approach this problem. Even though we're looking for molecular weight, we know that N, or the number of moles of gas, is in the formula. So we're going to say N is equal to the mass, which is 32.8 grams, divided by the molecular weight. Always remember that. The number of moles is equal to the mass divided by the molecular weight. Okay? So we're looking for molecular weight. So we're going to need that in our formula. Times the volume of 34.9, that's liters, of course, times the pressure of 12.50 torr, but that's not going to work in our formula. We got to have it in atmospheres. So we're going to do a little dimensional analysis right here. 1 atmosphere is the same as 760 torr. These are going to cancel away, and I'm going to be left with 1.64 atmospheres, right? And the temperature, I'm told, is 303 degrees Kelvin. Folks, it's already in Kelvin. That's good. That helps, right? It wasn't. If it was in Celsius, that'd be fine. I wouldn't have a problem with that, but I'd have to remember to do what? Add 273 to get into Kelvin. So now we've got it all. We've got N, at least a formula for N. We've got V, we've got pressure, and we've got 303 Kelvin for the temperature. Okay, so let's move on. Using PV equal nRT and rearranging, all right, we're going to say we're going to get N by itself. So N is equal to PV over RT. It's equal to N. See how that happened? RT just moved down. So PV over RT is equal to N. So now let's plug in. We've got 1.64, that's the pressure, times the volume of 34.9, divided by the R value is 0.0821, divided by 303 degrees. Let's do that together on our calculators. Ready? 1.64 times 34.9 equals, divided by 0.0821 equals, divided by 303, and what I get is 2.300824, but I'm going to round it to 2.3, okay? So 2.3, though, that's the number of moles. Remember, I wasn't being asked for the number of moles. What was I being asked for? Molecular weight, right? Molecular weight. So I'm going to take that 2.3 moles and say 2.3 is the number of the moles divided by is equal to 32.8 divided by the molecular weight. I'm going to rearrange to get myself the molecular weight. The molecular weight then is found to be 34.3 grams per mole. I've determined the molecular weight. That'll do it for this problem. I'll see you in the next one. Thanks. Bye.